Welcome to your lesson on integral calculus. So this is where we will be finishing off the course, is integral calculus. We just give you a small introduction on what an integral is and how to find some of the more basic types. If you already watched the PowerPoint, then you will know that an integral is all about the idea of finding area under the curve. But now we're going to talk about the mathematical methods in which we actually find them. So, one of the interesting things that we learn right away about integrals, one of the things we call them is an antiderivative. Okay, the antiderivative is from the name of the derivative, because if you look at this little box in the top right hand corner, if you wanted to use x squared as an example, let's say, I'm just going to focus my video here because I think it's jumping in and out. See if we can get a better picture there. There you go, it looks a little better. So, if you start with x squared, for example, and you differentiate it, you get 2x. So we know that from our previous studies of derivatives. The idea of integration and why it's called the antiderivative is because when you then try to take 2x and integrate it, what we find is that we get x squared back. Okay? So the reason that we call integration, sometimes we call some of our integrals antiderivatives, is because integration reverses the process of differentiation. Okay. So you're going to find that integrals and derivatives are heavily related, that they are in fact reverse processes of each other, which is pretty crazy when you think about what the two actually represent. Derivatives being the slope of curves, right? Instantaneous rate of change, slope of a curve, and here we are saying that the reverse process of that gives you area under the curve. Okay, which is, two pretty crazy ideas heavily linked together through a reverse process. But it kind of makes sense when you think about the video we had, right? We were trying to find we had the rate of change, we were looking for the amount, we were able to use the idea of area under the curve to get that, so we saw there that rate of change was related to area under the curve. So we did actually see that in the PowerPoint, that rate of change and area under the curve were related, which makes sense as to why we can say derivatives and integration are so heavily related. But it is pretty amazing that these two things are so, seem so different in concept and yet are so heavily related mathematically. So that is the idea here, though, behind integrals, is that you are essentially running derivative processes in reverse. So, first one, actually on that topic, before we actually get into this, let me just remind you, you do have to have a very good understanding sorry, I kind of butchered the word there, understanding of derivatives before we begin. Right? If this process is a reverse process of derivatives and we don't know derivatives, that's going to make this much more difficult, right? So make sure you have a good understanding of derivatives, what we mean when we say, dy, dx, what that means, how I'm finding derivatives. Because now that we're going to do the process in reverse, again, it's more difficult to understand why if we don't know what derivatives are. So go back if you need to. Hopefully you don't need to. You've got it remembered from last couple weeks. But like I said, if you need to, go back and have a look and make sure you remember what derivatives are. All right. Find the function for which the derivative is 8x cubed. Okay, so the idea here being we're going to find the antiderivative of 8x cubed. All right, so this requires a little bit of thinking, but we're going to go through it one step at a time. So your goal is to figure out, what did I take the derivative of that gave me this? You got to work backwards. What would I have taken the derivative of to give me that? Well, on first look, I would say I differentiated using the power rule. So I would say that since I'm seeing a power, I'm seeing a coefficient in front of the power, I feel pretty confident in saying that if I did do the derivative of something and it gave me this, it was the power rule that I would have used. So I had some kind of power, I brought it down in front, and I reduced my power by 1. Okay, so I know that that's the derivative rule that I would have used here. All right, so what does that mean for my antiderivative? Okay. So normally for antiderivatives, what we use is a capital letter. So if this is fx, we're going to write this. We'll just do it here. If little fx is 8x cubed, you might write the antiderivative with a capital F. Okay. So just like we have f prime or dy dx to show derivatives, sometimes what we do is we use capital letters to indicate integrals. All right, so what do I know? Well, if I decided that the power rule is what makes sense, I know that if this is the result after I took the derivative, so here's what my answer looks like now. This is what I want to know what it looked like before. Well, I must have reduced the power by 1, right? So if I reduce the power by 1, this is 1 less than it should be. So my power must have been 4 to begin with. Okay. So I know the 4 must have come down. All right, so that's what it looks like I took my derivative of. I must have taken a derivative of x to the 4. But then you realize when you do kind of a quick check that when you take the derivative of x to the 4, you get 4x3. Well, that's not what I have. I have 8x3. Okay, so obviously I brought down the 4 in front, and it must have multiplied with something to make 8. And I know that the only thing that 4 would have multiplied with to make 8 must mean there was a 2 in front of it. So now when I go through and check, and that is one of the best ways to check your answers, since integrals and derivatives are inverse processes of each other, if you get your answer for your integral, if you differentiate, so if you take the derivative of your answer, basically go backwards again, you should be able to get what you started with. So you can always check answers if you needed to. But again, to do that, you have to have a good understanding of differentiation, because if you don't know how to take a derivative and you try to check your answer, then you're going to think something's wrong when it's not, potentially. So if I check again, now I have 2x4. So if I do a quick derivative of that, I see that's 8x3. So yeah, that's what I used. So this is my antiderivative. Of 8x cubed. Okay? So this is the idea behind integration, is that we are trying to figure out the function before a derivative would have been taken. Okay, at least that's how we describe it as an antiderivative. Now, integrals themselves, it doesn't mean that what you're presented with is always an integral, a derivative, and you're trying to undo it. That's not necessarily true. Just the idea behind an integral process can be thought of as undoing differentiation. All right, antiderivative. So if you want, you can give it a quick pause and you could try this one on your own really quickly. So if I want to say that this is my current function after derivative was taken, so if fx equals x squared plus 2x, what is the antiderivative? So what is the function, assuming that this has already had a derivative taken, what would be the original function before that? Okay, so the antiderivative. All right, so if you want to take a quick second, pause the video and try it yourself. See if you can work backwards to figure out what would I take the derivative of that would give this, right? That's the idea here. What did you take the derivative of to get this? All right, So hopefully give it a try yourself. If not, that's okay. We're going to do it right now. I have two pieces. So again, based on my knowledge of derivatives, I know I would have taken the derivative of one piece and then the other. This isn't some reverse, quotient rule or product rule. This is, two pieces that use the power rule, first piece, second piece. All right, so if I work through it, again, in my head here, if this is the answer after I took a derivative, well, if it's the power rule, again, I know that based on the power rule, this is one lower than it should be, right? If it's the power rule, the number must have come down at front and reduced to 2. So this must have been 3 initially. If I do the same here and say, okay, well, if this is power of 1, x to the 1, I know that it must have been 2 originally because the 2 would have come down in front and this power would reduce to 1. So I know that both of these powers, based on the rule here, they were reduced by 1. So if I want to know what they were initially, I should increase them by 1 to get back to what they were. And I did. So the 2 became a 3 and the 1 became a 2. So now if I do a quick check and I say, okay, so at this point, what would my derivative be if I took it? So if I take the derivative to see if I get what I started with, I get 3x squared and 2x. All right, well, it's not bad because this is correct, so that's good. But here is a bit of a problem. I didn't finish with the 3. The 3 was gone. Well, where would the 3 have gone? I mean, there's supposed to be a 3 in front, so how can I not have one? Well, if it's gone, it must mean that it multiplied with something to make it, not be there anymore. Now, it doesn't mean it's 0. We're not going to say, well, there must be a 0 in front. That's what multiplies to make numbers gone. Remember, the number isn't gone. The number is just now a 1. What would I have multiplied the 3 by to give a 1? Well, if I give it some thought, I realize that if there had been a 1/3 in front and the 3 came down, the 3's would cancel and I'd be left with a 1, okay? Which is what I'm seeing here as a coefficient of 1. So there's a 1/3 in front of there. So now if I check again, I get 3 times 1/3 x squared plus 2x. And that's what I started with. So that works. So that's my antiderivative. Okay? So this is the idea, again, behind an integral, is that you are essentially performing, these types of rules, power rules especially, backwards, because they are inverse process of each other. Okay? So now, if you've gotten the idea of this, you're either, okay, I get the idea, I can add this and do this. The coefficients are a little harder to think about it. Well, you might be wondering, if this is inverse process of each other, how could I possibly inverse, the chain rule or the quotient rule and all those algebra steps? There's no way I can work backwards from all that. You don't have to, okay? There are different rules for integrals that allow us to do integrals that don't involve this kind of thought. Let's put it that way. We have rules like we do with derivatives, integral rules. So if you need to take an integral of a specific type of function, a log function or a power function or a trig function, we have rules specifically that allow you to do it quickly. Okay? You wouldn't have to sit there looking at an answer and figuring out how to work backwards to the quotient rule. That would be crazy. But I just want to give you an idea of how we can work the idea of an antiderivative, doing the process in reverse to get essentially an integral. Okay? All right, so how about we actually get into the talk of integrals now? All right. So the first type of integral we're going to talk about is the indefinite integral. We're going to talk about indefinite and definite, and those are going to be the two things we talk about in this unit, and that's it. Definite is pretty easy to extend onto, so I have that on the list for next week's lesson, but we'll talk about that at the end of this lesson, whether you want to jump ahead to it or not. But let's worry about indefinite for now. given the following functions, x cubed plus 4, x cubed minus 7, x cubed plus 4 pi. I want you to take a second and think about what do they have in common. Okay, especially when I think about integrals, derivatives, think calculus, what do they all have in common? Okay, so you might be saying things like, well, they all have an x cubed function, but think a little deeper than that. When you think calculus, what do you notice they all have in common? So hopefully you're having a quick look at it and you're noticing maybe they all have the same derivative, right? If you take the derivative of all of those functions, you will get the same answer, right? Now, that is a bit of a problem when we start to work with integrals. If you think about the fact that all of these have the same derivative, and what you just learned about the idea of the antiderivative, that could be problematic. So for example, if I asked you to figure out what did you take the derivative of to get this, you would tell me x cubed. But that's not necessarily true. What if it was x cubed minus 7 and the 7 was 0 and you didn't know? Or x cubed plus 4 or plus 4 pi, right? You wouldn't know whether or not those constants were there or not, right? Because there'd be no way to know for sure because they would just be 0. Or they weren't there at all and your answer of x cubed is correct. So this leads to the idea of the notation of an integral. So on that note, so here are 4 functions, okay, and this is what the idea of what I was mentioning above, so that x cubed idea. So here are your 4 functions that might represent the x cubed. Maybe this is x cubed here, this is x cubed minus 7, plus 4, plus 4 pi. They all look the same, the functions all look identical, but they're not the same, right? They're in different places on the graph. So how do we ensure that if we are trying to find the integral, and especially if it's area under the curve, I mean all 4 of those are going to give you 4 different areas under the curve, how do we ensure that we're giving the correct information? So here's how we do it. So first let's talk notation. So if you want to find the integral, you use the integral symbol. It's essentially a symbol for sum. It looks like an F. Okay, kind of like this. So this is the summation. We just use it, we call it the integral sign. This is called the integrand, and this is the variable you're integrating over. So just like with derivatives, this variable is very important. This is the one that you are saying, this is what you should treat as a variable. The rest should be treated as constants or coefficients. Okay, so it's entirely possible that you have multiple variables in a formula, but if you want to integrate over a specific one, in this case, x, you need to make sure that that's the letter in the dx. Okay, so pay close attention to that dx. It has to be there, and it has to be for the letter you are integrating over. Okay, so make sure that's there. In fact, these 2 symbols here always go hand in hand. So one of them should never be there without the other. Okay, so if you have an integral symbol, you have a dx symbol, or dt, or du. Those 2 things must always be in place together. And just like limits, they have to be on every line until you actually find the integral. When you actually find the integral, then it can be removed. So you do need to try to do all your integrals in one step in order to be able to remove the integral sign. So do pay close attention to notation, because that's something I'm looking for. Watch my notation in the examples when I have things there and when I remove them. On top of that, one other very important thing that goes back to this idea here of all of these examples above having the same integral, whether there was no constant or whether there was a constant. Whenever you do an integral, you're always supposed to add the constant of integration. Okay? This tells someone this is the integral of the function, this is the constant that might be included if necessary. Okay, so it tells someone to be aware that there could be a constant at the end of this formula. We just don't know what it is. All right? So make sure whenever you're performing an integration calculation that you include this constant of integration. So I'm going to do 2 examples at the end of this video to show you how you find this constant, if there is one at all. But for now, you'll literally just write plus c. So there's no number, just plus c. Okay? And that's, again, the idea is to say I don't know for sure whether there was something here, so I'm just saying there could be a constant. Okay? Again, it stems from this idea up here of taking the integral and you're not sure whether there's nothing or some other value. All right, so before we get into examples, because we're going to do that in just a moment, once I just read over these rules for you, we're going to get into examples. So an integration formula, there are a couple down here. I have a separate document as well with them included. These are the formulas I was mentioning for you to do integration. Okay, these are the only ones we're going to talk about. Again, we're going to stick to polynomials, so we're not going to do any trig, we're not going to do any logs or lns or exponentials, not in this course. You'll do more, especially trig, or anyone going on to Math 20. We're going to use these ones. All right? Now, just like derivatives, the main rule you need to focus on is this one right here. Okay? And you'll get used to it pretty quickly, just like you probably did the derivative rule. I bet you by the time you were doing, your examples of derivatives, you barely even noticed how often you were, bringing something down, putting it in front, and reducing your power by 1. You were just doing it so often, that was a rule you probably barely thought about. But in integration, you'll find it's the exact same thing. You're going to be doing that one over and over so much, you'll probably lose track of the fact you're even doing it. The other ones, though, I do want to just quickly mention. Again, you'll kind of see me doing them as we go through our examples, and they're not, they're not too hard, even though I would never, I would have given you these to you on a test anyway. I would have provided them to you anyway on a test. You'll probably find you'll barely need to look at them. There's only one or two that I find students sometimes have a bit of trouble with, but otherwise, like I said, once you do a couple of examples, you'll probably get pretty good at this pretty quick. So the one that I find that students have the most trouble with, actually I'm going to just go to the second one first, I'll come back to the first one. The one that students tend to have a bit of trouble with is remembering this guy here. Okay, it's not that it's a hard one to do, I think you just kind of forget. So just a quick note, if you integrate 0, you get a constant. Again, if you think about derivatives, that makes sense. What would be the derivative of a constant? 0. So basically, if you try to integrate 0, you're going to get a constant. Okay? Doesn't happen often. There's not a lot of functions that are literally 0, but it's something to keep in mind. And if you think about derivatives, that makes sense. All right, but let's talk about this one. If you take the integral of a constant, okay? If you take the integral of a constant, so say 5, all right? Again, if you think about derivatives in reverse, the answer makes sense. What would you take the derivative of that would give you 5? Well, 5x. So whenever you do the integral of a number, no letter, you add the letter on the end that you are integrating with. Okay? There we go. So for example here, I'll do a quick one if you want. If I was integrating 7 dx, my answer would be 7x plus c. So I would add an x onto that 7. I'm specifically adding x because it says dx. If I was integrating, say 2 dt, this would be 2t plus c. Okay? So if you have just a number as your function, you'll add on the letter. The letter has to be what you're integrating over, and you'll add your constant of integration. Okay. All right, other than that one, these last two, again, they're, I don't think you'll have any trouble kind of keeping them in the back of your head. So here, if you have a number in front of a function, you can, if you wish, bring that number out front. So you'll see sometimes I do it, sometimes I don't. There's no really reason why sometimes I do and sometimes I don't. You can or you don't have to. It really doesn't matter. Just what the rule itself means is if you see something like 5x dx, if you want to bring the 5 out, so it just sits in front of your integral and then integrate just the x, you can. Okay, you don't have to though. You can keep the 5 inside and just do the integral anyway. It doesn't hurt anything. It doesn't make a difference. Again, I don't really have an explanation of why you're going to see me do it sometimes and sometimes I don't. I think I mainly do it when I'm doing substitution, just so that because substitution has a couple extra steps on it, I just like to have it sitting out front so it's out of my way, and I'm not getting it confused with any other numbers. But other than that, I really don't bring them out. I don't think it makes a difference at all. This last one is similar to the derivatives. The idea here is if you have multiple pieces added, subtracted, you're just going to take the integral of each one. Okay, so if you have x plus 2, you're going to do the integral of the x and the integral of the 2. Okay, you don't actually need to separate them the way they have. Again, I don't. You're going to see when I do the examples, I don't separate them into multiple integrals. You really only have to do this if you're not going to do the integration in one line. The main thing is you have to keep the symbols for integration if you have not completely integrated. So just be careful with your notation. Make sure that if those symbols are still there, it's because you haven't integrated, and if they've been taken away, you've integrated the entire expression. Okay. So if you are going to do things, a little bit slower, one step at a time, yeah, you might need to separate each piece. Okay, but again, you'll see in my examples I never do, because my integration happens in one. I always do it all in one line. Okay, I just do one piece at a time, but I do them all in one step. Okay. All right, here's your last most important rule. Okay, before we jump to the examples. There's only 2 rules you're going to learn: power rule and substitution. And substitution basically is the power rule. So the power rule says if you have x to the power of n, well, you can imagine it's going to be very similar to derivatives, but it's going to be the opposite. So in derivatives, you took 1 away. Well, if your integration is the opposite, you can see your power rule here. When you integrate, you're going to add 1. Okay? And on the bottom, you're going to divide by n plus c. N plus 1. All right? So when you have something on the bottom, n plus 1, and then on the top, x n plus 1. Okay? And then at the end, plus c. Right? The only rule here is that you can't have x to the negative 1, so we can't integrate this guy. Right? Actually, if you do integrate that, what you get is ln x. Okay? So it doesn't follow the power rule, it follows the ln rule. So we don't do that one. All right? Any other power, though, is fine. It can be decimals, it can be fractions, it can be negatives, it can be positives. It just can't be 1. So that's our negative 1. Okay, that's our only rule. All right. So I don't really want to explain too much more than that. It's always easier just to, do the math instead of seeing the, bunch of formulas. So how about we just jump right in? All right. First example. Just before I start, I'll give you a little bit of a cautionary. Don't forget C. Okay, it actually kind of looks more like an E, doesn't it? Let's fix that up. Don't forget C. All right, it's very easy for students to forget C. Do make sure it's included. It's a very important part of your answer. And the other thing is just please watch notation. So even as I'm going through, you're watching what I'm doing with my numbers, but also notice how I use my notation, okay? And then where I have integral signs, dx's, and then when I don't have them, okay? Basically, you'll see as soon as the integral signs are gone, C is there. So you'll see integral, 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 integral sign gone, and a C is now there because I did the answer, okay? That would be a good way to kind of note the notation. All right. Okay, I want to integrate 2x. So according to the power rule says I am going to, first of all, I want to make sure that everything is in form of a power. So one of my very first steps would be to change or simplify the expression to something with a power. Okay, try, just kind of like with derivatives when you might try to simplify something right away to use the power rule because it's the easiest one to do. Same thing here. If something doesn't look right away like you can use the power rule, see if there's something you can do to make it look like the power rule. Whether you expand some brackets, whether you do some, fraction reducing, whatever it might be, see if there's a way to simplify it just to make a nice, easy power rule function, because that's the only rule you're learning in this class. So if we can't use the power rule, we don't have another rule to use. So let's make sure everything is in that form. So right now I'm good. I do have a polynomial with a power of 1. So according to the power rule, and it's already set up, it's simplified, I don't need anything else, I'm ready to take the integral. So the integral of 2x, well, the power rule says take the variable, the power on top, it's a 1, add 1 to it. So 2x, I'm going to add 1 to this to make 2, and I have to divide by this number here, n plus the power plus 1. Okay, so a nice little shortcut. So this is how I normally do it. So I look at my power, add 1, whatever's here goes here. All right, because that's what the power rule says. The power rule says that xn becomes n plus 1 over n plus 1. Okay, so this new power and this below are exactly the same thing. So once I look at my power, add 1, whatever that is, that's going to go underneath. Okay, it might get a little tricky at the bottom when we start doing fractions on the bottom. I'll help you with that, but that's my little, it's not really a trick, it's just something that's good to notice, that your exponent and what's underneath are exactly the same. Okay, so you can just quickly jot down the exponent after you add 1, and then the same number goes underneath as a denominator. All right, so that is my integral plus, very important, don't forget, c. Now here's where I actually performed the integral. I added 1 and I divided by n plus 1. Okay, so this is where I've performed the integral, which is why you now see the integral notation has been removed, because I performed the operation of integration. So because it's done and I did it, now those symbols, the summation, the integral, and the dx, can be removed. And once they're removed, plus c gets put on as well. Okay, so you should find that wherever these are there, and they might be on there for a couple lines, that's fine. As soon as you do the integral, you've got your answer. That's when plus c appears. Okay? And at that point, you can do any simplifying that you think you can. So those 2's can go away, and my answer is x squared plus c. Which again, if you want to do a quick check, if you take the derivative of this, you get this, okay, which is exactly what you should, because that's what integration is. Reverse process. All right, let's try one more before I start showing you put some fractions and negatives and all of that in there. So let's try it again. How about 3x4 dx. All right, so double check, can I simplify? Do I have something that I can just easily use a power rule with? Yep, that's good. I can go ahead and do my integration. So I have 3x to the 4, so the x to the 4, I know that the power rule says increase by 1, and whatever that new number is goes in the bottom. So I can't simplify that, so that is my answer. Okay? Again, I kept the, there's the integral symbols. As soon as I took the integral, applied the rule, I added c to get my final answer. You might be wondering about the 3, when you did the integral, you just looked at the x, you didn't do anything with the 3. It's because I didn't need to. Okay? In fact, one of the things you could have done, so again, this is what I meant when I talked about the rules. I don't do this. Again, there's no reason why I don't. I just don't. But remember, coefficients out front, they can actually come sit out front of your integral. Okay? So it literally means 3 times whatever this is. Essentially, it's telling you that coefficient has no impact. That's why it can sit out front of an integral sign. Okay? Because it doesn't impact the integral itself, not really. Again, I don't do it. I just, I know the coefficient just sits there. The number 3 isn't going to do anything. So I don't usually take them out. Sometimes I do, if I just kind of want them out of my way, because I have a more complicated integral. But otherwise, I just leave them in there. It just seems like one extra step we just don't need to do. All right, let's try again. Okay. How about a fractional exponent? Well, it's fine. That's no different. We can still work with it the same way we would anything else. All right, I've got 8x 3 over 2. It's a power rule. It's the only one we have. So when I integrate, I get 8x. Now I have to add 1 to this. So again, if you don't feel super confident with your fractions, just use a calculator. 3 over 2 plus 1 is going to give you 5 over 2. Right? And don't forget, though, on the bottom, you have to also divide by that fraction, 5 over 2, plus c. Right? So when it comes to doing the simplifying here, again, I know some are, really weary of fractions. Again, a couple things, either just use your calculator. See if I get it where you can see it. Okay, well, hope you can remember what's underneath. So it's 8 divided by 5 over 2. Okay, so if I put that in a calculator, hit this, I get 3 1/5. I'd rather have the improper, so I'm going to shift and hit that fraction button again, so I get the better fraction, 16 over 5. Okay. Now, you don't have to do it that way either. For those that are, you're okay with fractions, you're feeling, I don't really need to use my calculator, but I'm a little unsure about how to do this one. Again, the quick little trick. So when you have something like this, a number divided by the fraction, okay, what happens is that the bottom number, so this one here, multiplies with the top, and this one remains on the bottom. So you're going to see 8 times 2, it's flipping and multiplying. Okay, essentially what's happening here is you have 8 over 1 divided by 5 over 2, which is the same as this. Okay. So again, if you want to kind of do it quickly, because you don't need to show all this kind of work, if you want a quick way to do it, what happens with the number on top here, 8 multiplies with the very bottom number, the denominator, so 8 times 2, and the number in the middle stays in the bottom. Okay, so the top and the bottom multiply, this one stays in the bottom. Okay, so again, there's a couple little things. With enough practice you can get used to some tricks, but essentially imagine this flipping and it becomes 2 on the top, 5 stays on the bottom. Okay? But again, if you are feeling at all unsure, please just use a calculator. All right, but we do want fractional answers, not decimals. Try again. All right. Well, this one does not look like a power, does it? It looks like a quotient rule or a division or something that we used to use that quotient rule for. So what are we supposed to do here? Well, just as I mentioned, if it doesn't look like a power rule, see if you can make it look like a power for you. So this one, we actually know enough, I think, about roots and variables in the denominator, then we can change this into what we really need it to be, and that's x negative a half, right? We know that this means x to the half. We know that we can bring it up, make it negative, and do the problem that way. That looks a lot more like a power rule. So that's what we want to use. Notice too that my notation, I have not performed the integral. So these symbols still have to be there, and they have to be there together. You can't have one without the other. So notice I still have that integral notation, but in my next line, I'm actually going to do the integral, so it'll be gone. So I'm going to have 4. I'm going to add 1. So negative a half plus 1 makes a half over a half plus c. All right, one more line will do it though. We can simplify that fraction. So to simplify the fraction, 4 divided by a half, again, use a calculator if you're not sure, but 4, I know it's going to multiply with the 2, and the 1 is going to remain on the bottom, so I know it's going to be 8. So again, notice integral stayed. I performed the integral, so it was removed, plus c appeared. I simplified, plus c remained. Okay. Just like before, if you want to leave this as x a half, that's fine. You don't have to use square root. That's fine, just as it is. Alright, so I hope you're kind of getting a bit of an idea of how this works. Let's keep trying some more. So I have the integral of 8 minus 3x dx. Okay? So integral 8 minus 3x. So this is the first one where we've had multiple terms in our integral. Okay? That's fine. We have a rule for that. If you look back at the previous page, it just mentions, do the integral of each one individually. Okay? I don't actually split them up. Again, I kind of feel like that's needless extra work. We don't need to. As long as we recognize that we need to do them all individually. The only thing is, if you're not going to split them up into separate integrals, so what I mean by that is if you're not going to do it this way, okay, so if you don't want to split them up, you don't have to. You can if you want to. But if you're not going to do it, make sure you are doing the integration all at once. So in my next line, I'm going to integrate the the 8 and the 3x at the same time so that I can remove these symbols properly. Okay, you don't want to integrate the x and not the 3x, because then technically these symbols should be removed and then also technically kept, and it gets confusing. Again, I'm going to do it all in one step and then remove the symbols all in one. Okay. So when I integrate 8, well, if you remember from the previous page, again, sometimes this is the one that people forget. If it's a number with no variable, when you integrate, you get 8x. Okay, so you just add on the letter that you're integrating with respect to. Minus 3, this is a power rule. Even though you don't see a power, there is one, right? We know it's 1. So this is going to become, well, if it's 1 here, when I integrate, add 1, it's 2 over 2 plus c. So I did both of these pieces at the same time so that I could remove the sum and the dx, and as soon as I do the integration, I add c. Okay. And that one's done. So that's what happens when you have multiple terms. It doesn't mean anything, really extra special. Just do each piece one at a time as a power rule, and simplify a little bit when you're done. Okay. Again, if you want to do it this way and actually separate them into separate integrals, go for it. Just watch your sign in the middle, make sure it matches the sign between the terms. Yeah, that's up to you. Alright, this one. So having a quick look at it, hopefully well, actually you may or may not have an idea of where this is going. So this one you look at, and you kind of start to get flashbacks into, oh, this must be a quotient rule, and got to undo a quotient rule and things like that. But remember, we don't have that type of technique for integration. All we have is a power rule, and a power rule doesn't apply, to these types of quotients. We can just have a single power. So what are we supposed to do? Well, like I said, we have to simplify first. Is there something that can be done here? Yeah. This is something over a common denominator. Well, common denominators come from multiple fractions. So this can be split, okay? And I can do this because it's a common denominator on the bottom, okay? If there was, subtraction on the bottom, you can't be splitting up subtraction, but this is what this means, right? If you imagine putting these together, this is what you would get. So it makes sense I can split them. When I split them, things start to look, and I simplify, things start to look more and more like a power rule. The x squareds cancel, the x2 on the bottom can move to the top to be negative, and suddenly something that didn't look at all like a power rule looks like exactly what I need. Okay, so they might require some simplifying at the beginning. Like I said, you have no other rules except basically constants and powers. Anything else, we can't deal with that right now. So this is all we got. So everything should be able to be simplified and turned into a power somehow. So when I integrate this, which I am ready to integrate, I now have powers and I'm ready to go. So integrate 3, I know that's 3x because that's a constant and I'm integrating over dx. I am going to do the power rule here, so I'm going to add 1. Be careful, our brains tend to go the wrong way with this one. You see 2 and you add 1 and your brain immediately thinks 3, but it's minus 2 add 1, which actually puts you at minus 1. And a minus 1 on the bottom. Just be careful with those negatives, especially after doing derivatives. Our brains tend to go the wrong way with that on the number line. So keep an eye on those. And a little bit of simplifying. So 3x, those negatives will cancel, and I'll have 4 over x. And there we are. Alright, so at this point normally I'd be kind of stopping and giving you guys some practice and whatnot, but I guess, we'll keep going, but hopefully everything's going okay so far. We'll do some more with some simplifying, and then I'm going to show you substitution. Okay, so a couple more, and then we'll do some substitution, alright? But if at any point you start to think, at this point if you're starting to feel pretty, maybe a little bit confident about this, every time I write down the example, if you want to stop and try it yourself before I keep talking, go for it. Okay. All right, a couple more. All right, so this one. So again, you're thinking of derivatives, your brain starts to think product rules and chain rules and all that kind of stuff, and we don't have any of that. So our only option is to try to turn this into power rules. And right now, it really doesn't look like what all the other examples have, but it doesn't mean it can't. Okay, a power of 2 isn't too bad, and the x out front is, manageable. We can expand this, right? We know what this means. Right? We know that x plus 2 squared means x plus 2 times x plus 2. Remember, it's not x squared plus 4. Please don't write that. You miss the middle term when you do that. Right? But if I do expand it, and it does take a minute or two with your algebra, but once I do expand it, I get something that again looks much more manageable for what tools we have in our toolbox. Everything now is 3 terms of exponents, and that's it. So there's no brackets with exponents, there's no quotients, we have just things added or subtracted with powers, and that's all we can really handle at this point. So once you've taken the time to simplify anything that you could, you can integrate. So x cubed, add 1, divide by that same number. 4 squared, add 1, divide by that same number. 4x, add 1, divide by that same number, and add c. Okay. Again, notice I kept the integration signs the whole time I was simplifying, but as soon as I actually did the power rule, and I did it to all of them at once so that I could remove the symbols, then those symbols of integration left, and they left, and I added my c. Okay. All right, I am going to do one more quick line since I want to simplify that last piece. And there we go. So again, even if it doesn't look like a power rule right off the bat, you can expand it to. Again, we're going to talk though about substitution. That doesn't mean anytime you see a bracket or anytime you see an exponent, you should rush to expanding it, but it's just something to keep in mind, that you can just try to simplify something to utilize your powers. All right, after seeing the last one, you probably have an idea of how this one's going to go. So again, I have something, it's not really looking the way I need it to. I can't be having multiplication in here. I can only have adding and subtracting of powers. But again, that's not something that's a big deal. I can expand this so that I don't have multiplication anymore. So I'll get rid of the multiplication. This is x to the 1/2, we know that. So when I multiply the half and the 2, I add them. I get 5 over 2, x half. All right, so the 5 over 2 came from the half plus the 2, which is where the 5 over 2 is coming from. Okay. So again, it doesn't look like power rule right off the bat, but if you can maneuver things and expand things, bring them up, change the roots to powers, you can turn everything that you need to into power rule. All right. So I've got everything set up. I'm ready to integrate. So I add 1. When I add 1, I get 7 over 2 over 7 over 2. Add 1, I get 3 over 2 over 3 over 2. And the symbols of integration are gone, and I add c. Okay. Again, even if you don't feel super confident with your fractions, there's a lot of tricks out there. I don't want to again, I'm not saying I'm going to force you to do fractions in your heads, but if you practice them enough, honestly, there are so many tricks to it for you to do it quickly. For example, one quick thing you can do is, I know I have 1/2 here. Well, adding 1 is the same as adding a whole group of 2. So I know adding 1 is 1 plus 2, 3 over 2. I know here that adding 1 is adding 2, because a whole group is 2, so I know it's 5 plus 2, 7. Okay, so there's a whole bunch of these little tricks that if you do them often enough, honestly, it's not that bad to work with fractions, especially with integration and derivatives. It's all plus 1 and minus 1, and the equivalent of 1 is, that many denominator pieces. So again, with enough practice and you start to really find these tricks, things can go super fast. You really wouldn't need to use your calculator for much at all, right? You saw me jot down, 7 over 2 really quickly. It's not because I was sitting there in my head doing common denominators, and then processing it all. I just know that 5 over 2, when I add 1, it's the same as adding 2 pieces, because that's the denominator and that's what a whole is. So again, there's lots of little tricks. Try these often enough and honestly, you'll find them. All right, so one last thing, I don't want to leave it like this. I want to move the fractions to where they should be. So the 2 comes on top, so it's 1 times 2, 7 over 2 over 7. Essentially these are switching, flipping and multiplying. 8 times 2, 16 over 3. Okay, again, I know I go through the fractions quickly. You can use your calculator, but if you do it often enough, you start to see the tricks of, these are just going to flip and the bottom comes on the top. And, adding 1 is the same as just adding the denominator to the top number. So lots of tricks with fractions. You always have your calculator, but I know I can, with enough practice, you can do it faster than the calculator. So wouldn't that be nice to say, you're faster than a calculator when it comes to adding some of your fractions. All right, how about one more and then substitution? All right. How about a couple more fractions? All right, if you want to pause and try it on your own, go for it. If not, let's just finish this one off together. So I'm going to do one more quick line to simplify things so that I have what I need. It's going to be -1/2. All right, and as long as I've got powers, I'm not worried about, divided by 2. That's not a variable, so that's fine. I've got powers for my variables. No multiplication of variables happening, division of variables. I've got everything I need to do a power rule. So I'm going to go ahead, I'm going to add 1 to this. Again, I don't have to think too hard about it. It's going to be the top number plus the bottom number. So it's 5 over 4. Okay. Now I already have a number on the bottom, so that might make you feel a little unsure what you're supposed to do with the other part of this. Just leave the 2 on the bottom. Maybe you want to push it to the side a little bit. It is 1 over 2 after all, so you can say 1 over 2 on the left times the x 5 over 4. And the 5 over 4 can go over here. We'll deal with that after. Plus, add 1. So this is going to be -1 plus 2. That makes 1. So 1/2 over 1/2. And there we go. So we've got our answer, just an unsimplified one. So let's just quickly simplify that. All right, so what happens with this first piece? You've got a number here and a number here. So you have x over 2, but again, that is the same, even this, right? This is the same as 1 over 2, right? That is what's there, 1 over 2, 1/2. So you don't have to keep it under the x. You can push it off to the side if you want to. So 1/2 x 5 over 4. So what happens is the 1 and the 4 multiply to make 4. And the 5 remains on the bottom. Okay, so the top number and the very bottom on the denominator still multiply. And the number that would be left on the bottom, 5, is going to multiply with anything that's still there. So the 2. So you got 4 over 10. All right. So I got 2 times 2 here, and 1/2, and 1 left on the bottom. Okay. All right. And one last line here. There we go. Okay, but again, if you have any doubts about fractions, please just use a calculator, okay? I hate to see you struggling for 10 minutes to figure out a fraction when you do have a calculator sitting there. But since this isn't a test and you're just practicing, see if you can try some of my little tricks and see if they stick in your head and you don't have to, you're getting them right consistently. You might be able to do these pretty quick. All right, so I hope those ones have gone well so far. We are going to do the other half of the techniques. It's still power rule, but I'm going to show you how you can do some that are a little bit more complicated using something called substitution. So I'll get to that next. That'll be our last technique as well. All right, substitution. So substitution is for a very specific type of function. So you may be noticing, well, what if the function looked like this, or what if the function looked like this? You are really getting a very, just like derivatives, a very small set of techniques that are possible. There is a lot of functions that you could list or name for me, that they're not going to be able to be solved using either of these methods that I'm teaching you. But you're just getting an introduction into the idea. The important thing is to make sure you know what integration is. It's the idea of finding area of the curve. It relates to rate of change. And think of that PowerPoint that you hopefully listened to, and how we got this idea to use limits to find area, and brought about the idea of integration. Okay, so this is showing you just mathematically how we actually find these. So just like derivatives, try not to lose sight of what you're actually doing behind the math. Once you start putting numbers into these, what you're getting, crazy enough, is area under a curve. Okay, you're actually finding the space underneath a curve. That's pretty cool. And that's just one thing. You can do a lot of things like volume, work and force and pressure, and quite a bit. All right. So substitution is for a very specific type. It's when you're trying to integrate something. Okay, I'm going to use x squared plus 1 as an example. Okay. Substitution could be used to do something like this. So you might say, well, I'm certainly not going to sit here and expand this to the power of 4 like we did the other ones, and you're right, you're not going to. But one of the things that we can do is it's essentially, this is undoing the chain rule. Okay, so we're not going to learn techniques to try to undo quotient and product rule and all that stuff. But what this technique does is essentially undoes the chain rule. So this one would be for, if this is the function and I took the derivative of this, I might get 4x squared plus 1, and then times the derivative of the inside, 2x. So the 4 and the 2x multiply to make 8x. Okay? So substitution is going to be used to do something like this. All right? So one of the ways you can recognize substitution, okay? You might say, well, how would I know that this one should use substitution and not the ones that you just did that I had to expand all the brackets? How am I supposed to know when to do what? So substitution should be used. So some ideas on when you want to check for substitution. When you have a function inside of a bracket with an exponent. Okay, you might say, well, you had that a minute ago and we didn't use substitution. But here's the extra part. See if outside of that bracket you also have the derivative of the inside. So do you have derivative of inside? If yes, substitution. Okay, so when we do some examples, you'll start to see patterns into how they look. But the main thing with substitution is it's undoing a chain rule. And for the chain rule, for it to be the chain rule, a correct derivative of chain rule, it should mean that you had the derivative of the inside as well as the outside. So somewhere in that function that you're integrating, there should be the derivative, some form of the derivative of the inside. At least when it comes to the x part. It might not have the right number. For example, even if I had something like this, let's say. So even if I had this, you might say, well, that's not the, if I take the derivative of x squared plus 1 and the 4, that's not, the answer. It should be 8. That's okay. The number doesn't have to match, but what you're really looking for is the letters. Is the variable here on the outside, does the power on the outside match 1 less to the power on the inside, kind of thing? If I take the derivative of the inside, if I'm left with an x, I know it would be 2x, but essentially you're left with an x, a power of 1. Is there a power of 1 on the outside? Okay, so it's essentially just kind of keep in mind what would be the derivative of the inside of the bracket, and do I have something similar, maybe not identical, but similar on the outside, especially when it comes to the variable. The number can be different, that's fine, but we're mainly concerned that what's inside the bracket is 1 power higher than outside. Okay, so here the highest power is a square, here the higher power is a 1. Okay, so we're mainly concerned that what we see inside here, you know, when we take the derivative, we're going to get a power of 1 because it's going to decrease by 1, and we want to make sure we have that on the outside. So hopefully that makes some sense. I feel like I explained it in like 6 different ways there. I don't know if any of them make sense to you guys. I hope so. This is usually where I would, you know, we'd take some questions, and I hope you can see after we do some examples why I'm using the substitution rule for these ones in particular, why I wouldn't try to expand them. You'll see using the substitution, even if you make a mistake and you try to use substitution and you can't, there will be a bit of a red flag. Okay, so if you try to use substitution when you weren't supposed to, you'll know that you shouldn't have at some point in the answer. I'll show you where that point is. So even if you're not feeling 100% sure of whether you should use substitution or shouldn't, there will be a point when you try to do it that you'll get stuck and something will go wrong. Okay, so if that starts to happen, don't use substitution. Okay? All right. Let's give it a try. Alright, I had my first example, but it's a little bit of a harder one. I'm going to pick an easier one to start. So, let me see if I can find a slightly easier one. Let's see here. We'll do that one afterwards. There we go. That's a bit easier. Let's do this one. Alright, let's say I have 3x squared, x cubed minus 2, 6, dx. Okay. Let's start with that one. Alright, so this one, so when I look at it, you know, you kind of look at it and go, oh, you know, there's a lot in that. Again, hopefully your first thought won't be to try to expand this to the power of 6. Even if it's a power of 2 or 3, I mean, again, theoretically you could, even if you needed to use or could use substitution. If the power is low enough, you could expand it and just do it that way. But if substitution is possible, it is faster than trying to expand a bunch of brackets. How do I know that it is possible at all? Alright, well, when I look at the inside, okay, so first of all, I have something that kind of resembles the chain rule. There's a function inside of a function, a power. But when I look at the inside, I notice the derivative of this would be 3x squared. Okay, and this would be 0. That's exactly what I have on the outside. Okay, now you're going to see in the next couple of examples, they're not going to be identical. But the main thing I'm concerned about is when I take the derivative of this, do my variable parts match in terms of power? So if I take x cubed and take the derivative, I get something x squared. And I want to make sure that there's an x squared on the outside somewhere. Okay, I'm not as concerned about the number itself. I'm concerned about the power. Okay, you'll see why in just a moment. So this does look like a good candidate for substitution because the derivative power on the inside is 1 higher than the variable on the outside. Alright, so here we go. There is a couple steps of substitution. It does take a little bit longer than the ones you've done so far, but it is very systematic, very step by step, and if you follow the same steps over and over, they all go pretty smoothly. Alright, first thing is do what I just did. Check for substitution. Alright, so just check, you know, power on the inside, and anything on the outside. Is this higher by 1 than what's on the outside? And it is, so that's good. So here's what we do. Step 2. As soon as you decide that substitution is going to be your choice, you're going to use new letters. U and du. Alright, U. Substitution is substituting what you already have for something else to make the problem easier. So you're going to change whatever is inside the bracket. You're going to change that to be U. Okay, you're going to substitute it. You're going to substitute U in for whatever's inside the bracket. Then you're going to find du dx. Please try to write exactly this, du dx. I need to have that form specifically for the next step. It'll make it easier on you guys too. So don't use u prime. You'll have a harder time figuring out why I'm about to do what I'm about to do. So please use the du dx form, okay? So I'm going to find du dx. I'm going to differentiate u with respect to x. So when I differentiate this, I get 3x squared. Okay. Before you go on to your next step, well, I guess this is the next step. Before we get kind of back to the question, there's one more thing I want you to do. So you're going to find u. U is going to be what's in the bracket. I want you to find the derivative of it. I want you to call it du dx. Okay. Now it could be du dt or ds. It depends whatever's here. But it's going to be du, so u with respect to the letter. Find dx. So what I mean by that, now there's a really quick way to do this. I need you to just rearrange this for dx. Now the very quick way to do it, just remember that these two things switch places. Okay? So dx equals du over 3x squared. So a very quick, sorry, my voice there. A very quick way to do this, switch these two things around. Okay, so those two switch spots, that's dx. So dx comes up, this goes down. That happens every time. Every single time, just switch these two places around. So it goes du over this. Du over this. That's what dx equals. Every time. Just do it over and over again. Okay? All right. Alright, let's get back to the actual problem. So why did we do this at all? We did this so we could more clearly see how to apply the only rule we know, power rule, right? When you look at this and you think, you know, okay, how am I supposed to apply the power rule? I've got a power here, I don't know what I'm supposed to do with this. Here's where the substitution comes in, and here's how it helps. So if we go back to the initial problem, here's what I started as. Here's what I now know. I'm going to use these things here, these three pieces, to help me substitute in to here. So, what can I sub in? Well, I know that this is u, because that's what I said it was. What else do I know? I know that dx is equal to this. So I'm going to replace those two things. So sub back into the problem. Replace in question u and dx. So those are the two things you're always going to replace. You're going to put the u into your brackets, because that's what you denoted as u, and you're always going to change dx or ds or dt, whatever it is, you're going to change the dx to equal du over whatever it should be. Well, why did I do any of that? Well, firstly, the reason I changed this to du is because I can't integrate u over dx, right? I need to make sure that what I'm integrating over matches the letter that I want to use. So I had to use du instead of dx, but I can't just change it willy-nilly. I have to make sure that if I'm saying u is what's in the bracket, this is what du actually equals. What else? Well, you didn't substitute out this piece. Where are the u's in this? Well, there isn't a u in here, right? U is specifically equal to x cubed minus 2. That's not what this is. Does that cause us a bit of a problem? Not really, because here's where the red flag comes in. If you try to do substitution and you weren't supposed to. If substitution goes right, so if substitution is correct, all outside, okay, so all the x's on the outside of bracket, if there is any, sometimes there's no x's on the outside, if substitution is correct, all outside of bracket x's will cancel. And they do have to cancel, which means if you're left with even one x, that's a problem. Something has gone wrong somewhere. So my suggestion would be, if you don't find that your x's cancel, the first place I would double check is right here. I'd say most times, 8 out of 10 times, this is where the mistake is. You haven't taken the derivative correctly. You either forgot to reduce your power by 1 maybe, and that's the issue. So check here first for sure. If you're 100% positive you've done the derivative right and it's still not working, I would say the other 20% of the time the error is that you're using substitution when you shouldn't be. Okay, so that's where your red flag is. If you find your x's are not canceling and you're sure, you're looking at it like, nope, if they're not going to cancel, it's not going to work, check your derivative first, and if you're sure that's correct, I would rethink whether substitution was correct in the first place, because the only way substitution works is when those outside functions cancel. Okay, that's how the chain rule kind of works in reverse, is we have to cancel the outside derivative. Okay. All right. Now, in their example, not only the x's, but the 3's canceled. You may find that you do not have the numbers canceled. That's fine. Numbers don't have to cancel, but the x's do. So in this case, we are actually left with nothing but ux du, which is good, because now our very last, one of our very last steps is to use the power rule. So, do we know how to integrate something like ux? Absolutely. It might be a different letter, but the process is the same. So I know that if I want to integrate a power of 6, I'm going to add 1 and divide by that number and add c. So your very last step, try not to forget this one. I think you just kind of rush and forget. You don't mean to forget, but we don't leave the answer like this. Substitution was a method to make the question easier. It was not meant to literally change the variable. So u is still what u meant before. So we're going to change this back to x cubed minus 2 to the power of 7 over 7. And there it is. So this is our answer for substitution. Okay, so just like before, I kept the integral symbols, I keep the du until I perform integration. Once I perform integration, then I substitute the x back in for u. Okay, and I add my constant. All right, so that was our first example of substitution. Of course, I'll do some more, but that's our first example. All the rest will work exactly the same way with the exact same steps. So maybe have a quick look over those again, or just keep watching the examples, and we will keep going through for a few more. Okay? So you can see these ones do take a little bit longer to do. All right. Let's try the next. All right, second example for substitution. right, here we go. So, first of all, I don't want to leave right away. I just don't like the look of this. You know, I don't want a square root. I'd rather it be a half. I don't want this in the denominator. I don't know how to deal with stuff on the bottom. So right away, my first thought is, let's get all that stuff out of the bottom. Let's bring it up. All right, so when you look at this, you start to think, hopefully might start to think of substitution. Again, right away, my first thought something might be substitution is when I see a function inside of a function with a power. Usually right away I think of substitution, and that's at least what gets me to check it. You saw we did an example where we had x plus 2 squared. We didn't need substitution there. In fact, it wouldn't have worked if we had tried. Again, so it's not a foolproof plan, but the first thing to do is to see, do I have a function inside of another function, a power in this case specifically. So I'm really looking for, you know, that function, you know, a function inside of a power type of scenario. Again, it doesn't mean that that's every case that looks like that is going to be substitution, but that would be at least a, you know, like, you know, like better check. So how would I know if I should use substitution? I want to go a little bit further than that. So this looks like a good candidate, but I have to see about the derivative of the inside. So the derivative of the inside is just 2. So it's just a number. So that's good. So it's just a number. There's no x's on the outside, which is fine. You know, if this was x cubed, I'd be looking for an x squared on the outside, right? Because I'd have to have one less power, because I need the derivative of the inside to be somewhere on the outside, right, to undo the chain rule. So this is good. The derivative of the 2x, this is 0. Derivative of the 2x is just a number, so you know, there's just a number on the outside, or there's at least no x, which is all that matters. I don't really care what the number is. That looks good. So this looks like a good candidate for substitution. Again, even if you know, weren't feeling 100% sure, but you're like, yeah, I think, you know, the derivative of the inside is this, and it looks like it's on the outside, so yeah, I think I'm going to try it. Again, it'll, right when you try to get into the point of subbing u in and du, things will start to fall apart. If you start using substitution you weren't supposed to, you're going to end up with x's there that aren't supposed to be there. You're going to have nowhere to get rid of them. That's a big red flag. Okay, if you can't get rid of those x's, that means you were probably, again, either your derivative was wrong or you weren't supposed to use substitution in the first place. So again, use that as a really good red flag for you if something doesn't start to work out. All right, so I'm going to use substitution. So let u equal 2x plus 1. That means du dx is, well, what's the derivative of this? 2. Which also means dx is du over 2. Okay, remember, it's very quick to just quickly rearrange it. Try not to make the mistakes there. I've seen lots of mistakes happen just with rearranging. Don't overwork it. These two things just switch places. Okay, so dx equals du over 2. Okay, or look at it as, sometimes people look at it as dx equals du over 2. So whatever is here, du over this is what they get. Okay, again, there's lots of little tricks to make this easier, so you're not sitting there literally trying to perform the algebra. It's always going to be the same. These two switch places, whatever is here goes in the denominator. All right, let's try again. So we've got substituting it back in, 3, nothing happens to the 3. U gets substituted in. And I don't want dx there anymore because I'm going to be integrating with respect to u. So I want to change the dx to du. So dx is equal to du over 2. Okay. All right, so there's no x's to cancel. It's fine, it doesn't have to be, but as long as there's no x's remaining, that's what matters more. So that's good, no x's remain. I do have a 3 and a 2. They don't cancel, but there's a 3 and a 2 there. So this is really the only time where I do this. I mentioned this earlier. So since there's a 3 on top and a 2 on the bottom, the denominator, this is when I might pull them out in front, just so they're out of the way. So this is the only time I really utilize that that integration rule of pulling coefficients out front. Again, you don't have to, but I find it helps me keep track of, if there's a negative, sometimes there's negatives down here or a negative up here. It just helps me keep track of things a little bit easier. So if I do have extra numbers or signs with substitution, that's usually when I would pull the numbers out, just so that they're, again, just out of the way. All right. Other than that, though, I'm ready to integrate. So I've got a power. I've got nothing else, standing in my way. So let's do our integration rule. Add 1, divide by 1/2, plus c. All right, if I simplify a little bit, I have 3/2. This is divided by 1/2. So I know that the number on the very bottom ends up actually going on the top because flip and multiply. So this 2 is actually going to end up on top with the 3 to make 6, and 2 and 1 are going to make 2. So I have 3u½ plus c. And very last step, try not to forget it. The very last step is we don't want to leave u as our answer. We know what u equals. It's 2x plus 1. So I'm going to put that back. And there it is there. So there we go. The idea here being that if you take this derivative using the chain rule, you will get what we had initially. Okay? So this is the technique that undoes the chain rule. So you've learned the ones that will undo power rules. You've learned what will undo a chain rule, but that's where we're going to leave it. We're not going to be doing quotient or product. That undoes enough rules for this course. All right, how about one more? Let's see if I can find a good one here for you. Let's see. All right, I think I got one. That'll work. All right. Okay, so I look at this one. I see, a function inside of a power. So that's a bit of a, a clue maybe that this could be a chain rule type of problem. Again, it's not a guarantee. We did some that didn't, but let's see if we need that one extra bit of confirmation to see if this would make sense here. So I've got a function inside of a power. What do I notice about the derivative of the inside? So the derivative of x squared would be 2x. Okay. Do I have, the 2x on the outside? I don't have the 2, but I don't care about the 2. I care about the x part. And I do. I have an x, a single power of x. Good. So if this has a power of 2, there is an x outside with 1 less. Okay. That's exactly what I need. Again, I don't care about the 2, that it's not there. Doesn't matter. What I care about is that when I take the derivative and get 2x, that means that on the outside, if it's the chain rule, there should be an x term on the outside, and there is, so that's good. So this looks like a good candidate. All right, so I'm going to use substitution. And again, if I'm wrong, if you are wrong, you know, and you try it and it doesn't work, again, it will kind of fall apart when you start putting that u in there. So if that starts to happen and you go, oh no, I have an x left and I'm not supposed to, again, check your derivative first, because you might be right, it is substitution, you just made a mistake with the derivative. But if you're sure your derivative is good, the more likely then is that you're not supposed to do substitution. Okay? All right. So I'm going to try substitution. U is going to equal what's in my bracket. Du dx is going to eat the derivative of u. So what's the derivative? 1, that's 0. Minus x squared, that's minus 2x. Please watch your sign. That means, therefore, since I actually need dx to substitute back in, I don't want to forget I have to rearrange this. Again, very quickly, I know dx is du over minus 2x. Okay, again, I can do this very quickly. I don't need to do a lot of algebra or a lot of rearranging, not on paper. I know that dx is du over this, okay, because these two things just switch places. All right. So when I go back to the integral part, and I put u in, so the only things I'm subbing back in is I'm subbing in u for the bracket, and because I'm going to be integrating over u instead of x, I need to replace the dx with what I found over here, du minus 2x. All right, how am I doing? Well, I need to integrate over du, which means I can't be using other variables. And right now I have x's in there, but if I did it right, and it is substitution, the x's should cancel. And they did. Did the 2 cancel? No, it doesn't have to. I'm just concerned that the x's are gone. And as long as the substitution was the correct choice, they should. And they did. All right, so I have u7 du over negative 2 left. Again, just like before, when there's numbers in the bottom and signs and extra numbers, this is when I do like to use that extra little bit of that rule and pull everything out. So this does mean there's a 1 on the top, a 2 on the bottom, 1/2, and there's a negative sign. So negative. Again, it doesn't matter where the negative goes, top or bottom, makes no difference, but this is negative. Again, if you're wondering where the 1 comes from, remember if you don't see it, there is a 1 there. So 1 over 2, negative. Negative 1 over 2. All right. I can go ahead and integrate. I got a power rule, power 7, add 1, divide by what's there. All right, and I have negative u8 on the bottom. I have 2 times 8, 16, and plus c. And my very last step, I don't want to leave u there. I want to have 1 minus x squared. And there it is. All right, so I hope that works for you. If you want, you can stop here and kind of go to the practice. If you're just curious, I think I'll just do one more substitution just for the heck of it. But if you've got the idea, you can stop the video here and go on to practice. Before you do stop the video, if you choose to, I've already posted the video for next week, our final week. It is relatively, I don't know if it's short necessarily in time, but the concept is relatively simple of what we're doing next week. So if you do want to just kind of finish off the material and, be done with math lessons, if you're not too exhausted of math today, if you've got some time later today or even tomorrow, whenever, I would go ahead and just watch it, finish it off. We're just going to basically now be putting in some numbers and evaluating, and I'm going to show you how you can find that C. So there's really not a lot more in terms of math. You're just going to do it like one extra step further. So it was going to be a short lesson anyway if we were in the classroom face to face. So again, if you just want to finish it off, go ahead and start the next week. Okay, you don't need to wait. This will get it off your plate. All right. Otherwise, I'm going to do one more quick example of substitution for anybody that just would like to have one more because they're still not 100% sure. Okay? All right. Okay, how about one more? So right off the bat, I do not want to have that bracket on the bottom. Okay, no matter what technique I decide to do, I don't want that bracket on the bottom. So I'm going to just quickly throw that up top. All right, I'm going to see if this looks like something I would want to do substitution with. Well, I'm actually, sure I'm going to have to use substitution, even without doing a lot of checking. This is not something I can expand. This is not power of 2 or 3. This is -3. That can't be expanded using algebra. So unless I substitute this, there's no way I can solve it. So right away, even without checking the derivative, I will, but I know right away that there's just no way for me to simplify this otherwise. But if I do also check the derivative on the inside, the derivative is 2. There is no outside x term, and I don't have any outside x terms, so I would be good there as well. But yeah, I'm 100% sure I have to use substitution. I have a function inside of a power, and that power is negative, and there's no way to simplify it otherwise. So definitely going to be using substitution here. So we're going to let u equal the inside. We're going to find du dx. So what's the derivative of this? This is 0. This is 2. And I'm going to need that rearranged, okay, to be, dx is equal to du over 2. All right, so these are the two pieces, I need the most. I need that and I need that, because those are what are getting substituted back into the equation. All right, back to the question itself. So back to here. I have integral of 8. I'm going to change the inside. So I'm substituting the inside is going to be u, -3. And I'm changing dx to be dx du over 2. All right. If there were any x's, I would cancel them, and there shouldn't be any left. They should cancel. I notice I have an 8 on the top, a 2 on the bottom. I'm just going to simplify that quickly to 4, and I'm going to bring it on the outside. Okay. And I have a nice looking power rule. So u to the power of -3, I'm going to integrate that. So u -3, I'm going to add 1. Be careful, adding 1 to -3 actually makes -2 over -2. Plus c. If I simplify the 4 and the -2, I get -2, u -2. And last but not least, I don't want to leave the u as it is. I'm going to substitute what I had as u back in. If it's alright, I'm going to also just get rid of the negative right away. So you're going to see in my next line, it's going to just shift to the bottom, and it's because of that negative there. So -2, the number stays on top, but the 3 plus 2x to the power of 2 goes back on the bottom. So I did two things at once there. I put the u back in, and I also made the negative exponent back to a positive by going down. But there it is. And that would be my answer. And I have my plus c. Even in substitution, you need your plus c. So I hope that other extra example was helpful. You could do some practice if you wish. Like I said before the example, if you're if you just want to plug along and finish things off, you can go ahead and start next week's stuff as well.